In this video, we're going to talk a little bit more about ionic bonding and ionic compounds, specifically how we can determine the formula of an ionic compound if we know what ions are involved, and what we call them. All chemicals have names. The naming system is very specifically spelled out with certain rules. So we're going to talk about how that works for ionic compounds because it is different for ionic versus covalent. So ionic compounds, for the purposes of this course, contain one type of cation and one type of anion. In the world at large, you may have more complicated ionic compounds can exist where there are multiple types of each ion, but we're not going to deal with those. We are talking about what are known as binary ionic compounds, which means they just have two elements or two types of ions involved, one positive and one negative. So we have one kind of cation, we have one kind of anion, but this doesn't necessarily mean there's exactly one of each, because ionic compounds must always have a total charge of 0. So depending on what types of ions are involved, we might have, say, a +1 cation with a -2 anion. Those don't add up to 0 as is. So what we need to do to write our formulas correctly is we adjust the number of each type of ion to make that true, to make the sum of the charges 0. So let's look at a couple examples. So first off, really simple one. What happens when sodium and chlorine come together to form an ionic compound? So we know from the previous unit that we can predict the charges on these ions just from the positions on the periodic table. Sodium, being an alkali metal, likes to form ions with a +1 charge. Chlorine, being a halogen, likes to form a -1 charge. So in this case, because our charges are equal in size, they already add to 0 if we have one of each. So that means we don't need to make any ratio adjustments here. So we always want to use the lowest numbers possible, so kind of put our ratio in lowest terms. Is just the convention in chemistry. So if we wanted to write the formula for the compound that forms between sodium and chlorine, it would just have a sodium and a chlorine, and that is all. So it is true that, one of each adds to 0, so would 2 of each, so would 6 of each, but we always want to keep things in lowest terms. So the formula of an ionic compound shows the lowest ratio, the simplest whole number ratio of ions of each type. So in this case, 1:1 gives us the formula NaCl. By convention, we always write the cation first. So whatever is written first is going to be the thing with the positive charge, which is generally going to be your metal. So let's look at a slightly more complicated example. How about, what formula do we get when we combine calcium and chlorine? So same anion, different cation. We have a -1 charge on the chlorine because it's a halogen. Calcium is an alkaline earth metal. That family likes to form +2 charges. So now we have the sort of imbalance in charge. If we put one calcium with one chlorine, our charges don't add up to 0, and this is where we need to make some adjustments. We have 2 positive charges on calcium and only 1 negative charge on chlorine, means we need to have 2 chlorine for every 1 calcium in order for the charge to add to 0. So the way we show that in the formula is using a subscript. So our cation calcium comes first, our anion chlorine comes second, and to show that we have 2 ions of chlorine, we put a subscript of 2 after that element. So whatever comes after is always referring to the element immediately before it. So subscript after element indicates number of atoms of that element in the compound. You will notice that we did not use any subscripts up here, and I do not have a subscript after calcium. A subscript of 1 is implied. We don't explicitly write it. So the fact that there's nothing here is telling me that this subscript is 1. So anything that doesn't have a subscript after it, there's just 1 atom of that type. So by using subscripts to adjust our formulas, we can make the charge equal to 0, which always has to be true for an ionic compound to be valid, for that compound to actually exist. So the last thing I want to look at briefly is how we name things. So Ionic nomenclature is just a fancy term for how we name stuff. Pretty simple, really, in that what it boils down to is that we name the cation first, followed by the anion. And that's essentially all there is to it. So then it's just a matter of how do we name the individual ions, which is not always just the element name. So for the cation, it pretty much is. The cation name is just going to be the name of the element. There's also something known as polyatomic ions, which we will talk about in a future video. I think the next one, but a future video. But more on that coming soon. So it's the name of the element or the polyatomic ions, which are just this is what it is and this is what it's called sort of situation. There's not a lot of understanding to it. The anion is the one where it's a little bit different. If it is just an element, just a single atom, we change the ending on the name. So we take the element name, but we use it with the ending changed to "ide." So the last syllable, or sometimes 2, of whatever your element is, just gets replaced with "ide." So for instance, for the 2 examples that we just did, we did NaCl. Na is sodium. A sodium ion is just called a sodium ion. Chlorine became an anion, which we call the chloride ion. So the name of this compound is sodium chloride. So whatever the last part of your anion's element name is gets replaced with "ide." So chlorine becomes chloride. So this other example that we did would be calcium chloride. With the anions, sometimes it gets a little bit weird with how exactly do I replace the ending, like what constitutes the ending. For most things, it's the last syllable, but for something like oxygen, so the formula for sodium with oxygen ends up being Na2O. You can prove to yourself why that is. We would call this sodium oxide. So a lot of it comes down to just like what sounds good, which unfortunately is not a super systematic way to do things. With oxygen, the "igen" is what's being replaced. So there's actually two syllables that are being replaced with that IDE ending. But if you just kind of think about like what sounds sort of normalist, like normal-ish, like oxide kind of rolls off the tongue pretty nicely. Oxygide would be weird. If you tried to just replace the last syllable, it just sounds funky. That being said, I wouldn't take off points for it because it's kind of arbitrary. If you put oxygide on a quiz or a test, I personally would accept it. It is showing that you understand that you're replacing that IDE ending. The finer points of exactly what that ends up being, you'll pick up as we go along, and I'm not too concerned about it. So looking for like basic concepts is the point here. So this is kind of the basics of naming ionic compounds. There are a few weird situations, particularly with transition metals and these polyatomic ions that I mentioned, that we will get into in future lessons, but that is all for now.